Thank you for giving me the opportunity to share our results in this online meeting. I'm Yuh Tsunetoe, now a postdoc at Shanghai Astronomical Observatory, SHAO, and I here serve as the co-lead of the BHEX Japan Horizon Scale Physics Working Group. And today, I'd like to introduce some of our group's recent progress, and then I'll also talk about my own work on jet modeling. So I'm going to start with the study on ring images, which is led by Mikiya Takahashi at Tokyo Kosen. Their current topic is constraining the black hole spin by analyzing the time variability of the crescent-shaped shadow. As shown in the movie on the left, the crescent shadow is formed by the combination of photon ring and foreground emission coming from the inner accretion flow all the way down to the ISK radius, and the spin information is imprinted in this characteristic shadow shape. In this study, the authors combined two observables: the elongation of the intensity centroid orbit, shown by magenta dot in the movie, and the average width of the crescent shadow. In the diagram on the right, by crossing these two constraints, represented by the red and blue contours, we can reduce the uncertainties due to mass accretion rate variability and obtain a more reliable estimate of the spin. For instance, if we only measure the crescent shadow width and obtain a value of like 2.2 Rg, there remains a large uncertainty in spin ranging from 0.6 to 0.998. Then, by additionally tracking the image centroid and finding, for example, an elongation of 4.2, we can uniquely identify the spin as 0.9. So next, another focus is testing deviation from GL using MHD simulation and radiative transfer in a modified spacetime. And Kotaro Moriyama and collaborators ask whether such deviations leave clear imprints even under complex and turbulent magnetized accretion flows around the black hole. And they introduce the Retzola-Zhidenko or RZ metric, which is parameterized to describe deviation from the Schwarzschild metric. In the figures on the right, plasma and alpha velocities are plotted for three different metrics. The center shows the classical Schwarzschild case. The left shows the RZ metric with a stronger gravitational potential, and the right shows the RZ metric with a weaker gravitational potential. And as expected, a stronger gravitational potential leads to a slower velocity profile. And they also calculate ring images and light curves using radiative transfer in the modified metric. And they find that such deviation can produce systematic difference in light curve variability. As in the right, we can see that their stronger gravitational potential leads to a smaller variability. In this way, their work highlights the importance of exploring deviation from GL when interpreting the variability observed in Sagittarius and other sources. The next topic is about exponential frequency redshift close to the horizon, which is studied by Hiromi Saida at Daido University. When light is emitted from a region close to the black hole, the observed frequency decays exponentially with time, as shown in this formulae and schematic picture. And it is also shown that this exponentially redshifted signal should appear as a thermal-like power spectrum, like this. So from this, we can estimate the surface gravity or an equivalent temperature, as shown by this equation. And measuring this would provide a new and independent way to constrain the mass and spin of black hole without being affected by plasma environment. And also, simulation of fluid analog system have been performed, hinting that BHEX observation could try to detect them. And finally, recent East Asian VLBI network observations have suggested periodic motion in the M87 jet, which could hint at a hypothetical secondary black hole. If such a binary system exists, the gravitational waves it produces must stay below the background detected by non-grav. So, Moto Kikino at Kogaku University and colleagues have evaluated this scenario linking the observed jet precession to gravitational wave constraints. They find that, assuming an orbital period about 11 years, the binary mass ratio would be limited to a few percent. So this work highlights the importance of investigating contribution from nearby sources to the gravitational wave background. So from here, I'm going to focus on my own recent work on anisotropic electron distributions in jets, which naturally produce the rim lightning seen in M87 and other sources, as also introduced Ramish's talk. Here the question is, what can BHEX high-resolution images and movies teach us about jet physics when such anisotropy is present? So I'd like to start with our primary target, M87. Here I'm showing movies for 4 spin values at BHEX resolution. As you can see, the high spin cases in the 2 panel on the right produce persistently straight, wide jet, while the 2 low spin black hole on the left shows kind of wobbling or precessing narrow jets, often with a visible counterside emission. What's puzzling and interesting is that existing large-scale observations shows a wide jet with precision and bright counterjet, which creates some kind of tension in determining the spin value. In this regard, detailed BHEX observation of the innermost region, connecting the black hole to the jet launching region, should help resolve this contradiction. So next, let's look at the nearby jets, M84 and NGC 4261, which was also mentioned in the Angel's talk. And BEX can observe these targets on a scale below 1000 gravitational radii. On these scales, we can also create movies based on GRMHD model, just as we do for M87. And these sources have relatively large viewing angle, around 60 degrees, and they show twin jets with possible helical structure, making them excellent laboratories for probing the magnetic field geometry inside the jet. Another interesting feature we can explore here is magnetic flux eruption. After a major eruption event, the magnetic flux can rotate around and escape from the black hole, producing some filamentary structures in the jet by the jet, as shown in the movie occasionally and and also highlighted in the 2 panels on the right. At BEX resolution, these filaments should be detectable, and this signature would allow us to test the strong variability unique to MAD, as well as the dynamical evolution of jets around eruption and flaring events. So, we also investigate more distant jets, such as 3C273 and 3C279, which BEX can observe on scales of tens of thousands RG. And for this regime, we apply semi-analytical force free model to study the jet structure. These sources are nearly face-on, with a small inclination angle of about 3 degrees, and their jets shows a symmetrical double-edged appearance. And in these models, we set the terminal Lorentz factor of plasma bulk, while taking into account the braking effect of plasma inertia. And for the image shown here, we adopt Lorentz factors estimated from the apparent motion of blobs in these jets. But we should keep in mind that the velocity of blobs may not represent the typical or steady flow speed in the jet. So here, I further calculated images with different terminal velocity or terminal Lorentz factor. Here we set the terminal value is 10, 30, and 100. And one important result is that if the terminal Lorentz factor is too high, like 100, the jet becomes less extended compared to the lower terminal value, as seen in the right panel. This is because the Doppler factor for nearly vertical flow actually peak for the Lorentz factor of about 10, 20 to 30 when the inclination is small, like around 3 degrees in these sources. This means that by carefully monitoring the jet's extent with BHEX, we can directly probe its acceleration profile of the essential plasma flow, not only outstanding blobs. So finally, we also consider another source, Centaurus A, on scale of thousands of gravitational radii and with an inclination of 45 degrees using force-free model. We can see a twin limb-brightened jets, similar to what is observed by the EHT. And also, interestingly, the base region of the jet is optically thick, and because of the high mass accretion rate onto the black hole. And the intensity peak appears downstream along the approaching side, the upper one. This shift in the peak intensity location is also seen in observations and may support the scenario of jets launched from the highly accreting black hole. In this way, BHEX observations can help us explore not only different spin values and viewing angle, but also diverse accretion scenario. So, in summary, we study black hole shadows and jets, from spin and gravity tests to jet structure and accretion, to fully exploit BHEX horizon scale imaging. Thank you very much for your attention. I'll stop here.
Eh, Uh, Thank you very much. That was great. We do have time for a couple of questions, so let me start with Alex.
Hi, you. So I guess that everyone has been saying how great and useful this model is. Let me be the next one to say this again. Thank you for developing these models that you've mentioned. I guess my next question is, they've proved very useful so far. Is there an obvious next step to improve them? I mean, there's kind of a balance between keeping the models simple enough,
Mhm.
but
I
is there
think
some kind of other thing that you want to add to them?
okay. One how say one must do application should be slow, right? As also mentioned by Ramesh. And on this jet launching region, plasma is getting relativistic and being accelerated into the relativistic regime. And in this regime, the how should I say the jet evolution while the light rays are propagating in the emission region will be of importance, and we have to consider it. That these images I showed here is still stay in the fast traditional fast light calculation. So yeah, it should be there. Absolutely, should be the next step we should proceed with.
Fascinating. Thank you for pushing on this, Hugh. It's really good work.
I'll do my best.
Angela?
How worried should we be about plasma anisotropies in the disk?
Mhm.
Do
Yeah,
we
that's
think that, yeah, is it more or less important there? And have you looked at the images?
okay. One important takeaway is maybe in these some sources with a larger viewing angle. Maybe okay, as you can see, in these sources with large viewing angle, the how should I say the accent between reach and edge is not so enhanced, unlike M87. So I believe there in these sources, if we want more, how should I say, strongly accented twin sources, we should introduce the anisotropy inside the disk as well as jet. Or and
Mm.
absolutely, actually, our final stage should be something like that we implement uh, how should I say, anisotropy in thermal and non-thermal electrons, both in jet and disk region. Now we simplify non-thermal jet and thermal disk. So in summary, in the disk region, actually the anisotropy will also have an effect, and yeah, it should be also the next step for us to take.